Bismillah ar-Rahman ar-Rahim. Good afternoon, guys. Today our lecture will talk about the heat and cold in medicine. But at first, like the previous lectures, we will take basic information, basic physical information about the heat and cold. After that, we will create our link with medicine field. Let's take a look to the next slide. The contents talk about, like I said before, physical basic of heat and temperature, the T scales, units, Celsius, galvanite, Fahrenheit, how we can convert 1 to 1, thermal expansion, what that's mean, linear thermal expansion and its coefficient, the temperature and fillings, what the interaction between the temperature and the fillings, the way to measure the temperature. The tools. We have 3 tools. We will talk to all of them and explain each one. And at last, we will do a comparison between them. What the different, between the 3 different tools of temperature measurement. Let me take a breath and start with the first slide. At first, we should try to understand the temperature from molecular scale. What the temperature can do on the molecular scale. Actually, it can make a motion between them. Let's take a deeply idea about what is the motion molecular scale. Molecular are in motion in gas and liquid. We know that. But the surprising thing, it's the same situation with the solid, but it's not clearly like gas and liquid. But we have motion molecular at solid when temperature is increased. The molecules have some motion about their sides. The molecules move means that they have kinetic energy. When I say motion, molecular motion, what does it mean? That means kinetic energy. And this kinetic energy is related to the temperature. Sure. Here, the average kinetic energy, of the molecules of an ideal gas, liquid, solids can be shown to be directly proportional to all of these 3 states of the material, of solid, not of solid, because I said all of these 3 states in anything in our world is related with the temperature. Now let's talk about temperature scales. Like we know, the most famous one is Celsius, Fahrenheit. The last one is Kelvin. We will know the function to all of them. After that, we will learn how we can convert one to another. All measures are defined by the freezing point of water and boiling point of water. Like we know, 100 Celsius and 0 Celsius at freezing point to water, 100 Celsius the boiling point of water. Both of them, it's calculated by depending on water. Okay, at standard atmospheric pressure, the Kelvin is an absolute scale. It's some difference when we use Celsius and when we use Kelvin. By using Kelvin, I can use a most widely range of temperature. The most simple example is the absolute value, absolute 0. That's mean minus 273 Celsius. Let me keep going. It's directly proportional to the average kinetic energy in ideal gas. It fixes the absolute lower limit. Lower limit, like I said before, of 0 at 0 Kelvin, that's mean minus 273. It's a crucial point. The human couldn't reach degree less than the absolute zero because that they call to it the absolute zero. Here, the function of the temperature at Kelvin units equal temperature at Celsius plus 273. That's mean what? The boiling point is 100 Celsius. By that, at Kelvin will be 373. At freezing point, water, it's 0 Celsius. By that, will be at Kelvin will be 273. Here, we can convert this function to Celsius. Just will be temperature at Celsius equal T at Kelvin minus 273. At convert to Fahrenheit, the situation will be different. We will use another function. This function is temperature, Fahrenheit temperature equal 9 divided on 5 multiple temperature, Celsius temperature plus 32. And to calculate the temperature, Celsius temperature from Fahrenheit temperature, that will be TC, that's mean temperature at Celsius, equal 5 divided on 10 to what? To temperature at Fahrenheit minus 32 between two brackets. Now, we have simple note. If I want to calculate or determine, convert the temperature at Fahrenheit, I must find the temperature at Celsius. If I have it, but in Kelvin, that's when I convert it to Celsius. After that, I can determine the temperature at Fahrenheit. Here, this slide, the important information are started. The oral environment temperature. The oral, that's mean inside my mouth. In the oral environment temperature, it is not constant because why? Because we eating every day, we drinking every day. All of these foods, drinks have the different temperature, cold, hot, depending on what you are drinking, eating. By that, your mouth temperature is increase, decrease according to that. Dental bulb, talking about your teeth, is very sensitivity to the temperature. Maybe damage. Here it's important. You must focus on that. Maybe damaged if the temperature increasing steps will be more than 5 Celsius. That's mean to protect your teeth healthy, the temperature increasing must be like steps. Each step should be not more than 5 Celsius to protect your teeth. When you work on patient teeth, you must focus on this function. You must focus on this statement, okay? So the dental drilling rises when you will work on some dental teeth. Rises in temperature of bulb during drilling should be less than 5 Celsius. It's important, I repeated that. You must note that. Here we have example to learn how we can convert the temperature units from 1 to 1. Body temperature can increase from this temperature to this during extreme physical exercise or during viral infections. Convert this temperature to Celsius and Kelvin and calculate the difference in each case here at Fahrenheit. You must determine that at Celsius unit and at Kelvin. We will use this function, like I said before, at Fahrenheit equal 9 divided on 5 multiple Celsius temperature plus 32. By that, the Celsius equal 5 divided on 10 to Fahrenheit temperature minus 32 between two brackets. By that, you can calculate these results. And at Kelvin, like we know, equal Celsius plus 273. By that, the room temperature is 27 at Celsius and equal 300 at Kelvin. Note when we ask you to calculate the Kelvin temperature from Fahrenheit, you must calculate the Celsius temperature first. Here, the thermal expansion. Most material, like bridge, cables, anything, any material, specifically solid material, by increasing the temperature will expand and will contract when the temperature will decrease. Okay, we have expansion at temperature increasing, we have decreasing when temperature decreased. By that we have here thermal contraction when the temperature decreased. When the average kinetic energy or speed, what that means speed? That's speed, that's mean we have kinetic energy. By increasing the speed, the kinetic energy is increased. Of atoms is increased, they experience strong collisions. When the kinetic energy is increased from this state, from this picture to this picture. What that mean? That mean the kinetic energy is increased. By that, what will happen? The collisions will be more strong, okay? By that, when we have collision, that means the distance between these atoms are increased. Assume no change in the phase thermal expansion, just the kinetic energy, that's mean the speed. After that, the collision will increase according to the temperature. By that, the distance between these atoms increased too. Here we have linear thermal expansion coefficients. For example, the cables. Why the cables are expansion at the winter? Why the cables are at the summer? Sorry, the cables are expansions. We have expansion cables at the summer, and we have contracted cables at the winter. Why? Because the temperature changes. Here, for metals, building, bridges, cable, and let's take a specific example to your department is the dental filling. The dental filling is material, solid material. That means it has a sensitivity to the temperature increasing or decreasing. And like I said before, here at oral environment temperature, the oral environment teeth temperature is very sensitivity to the temperature change. Like I said before, let's come back to our slide. Here will be more specific in your oral environmental teeth by using dental filling. Like a good example, bar of initial length L to delta L. What that means? That means I will have L2 change when it's T changed by amount of delta T. We know what that means, delta T. Coefficient of linear expansion of the material is defined as alpha. What that means, alpha? It's a fractional change in the length. That means I have L2. By that, I have delta L because L2 is more or less L1. Change in the length over fractional change in temperature. By that, alpha, the linear thermal expansion coefficient, equal delta L divided on L divided on delta T, because we have two temperature, the first one, the last one. By that, we can calculate the delta L by saying delta L equal multiply L coefficient of linear thermal multiple delta T. Original length change in the temperature, the coefficient of linear expansion. Here, let's focus on the relation between the temperature and the fillings more. In restorations, when you will be a dentist, that will be one of the most important things you will do. It's a great business, has a huge customer numbers. Decayed dental was removed. What does mean decayed dental? It's the part who it has a damage, okay? Because the patient is not focused on his or her teeth, doesn't matter. Some disease in her or his teeth. By that, your job to clean that, to drilling that, and put the fillings. Okay, let me come back to my topic. You will remove the damaged part on your teeth, on your patient teeth, doesn't matter, and replace that by using fillings. Okay, here it's important, you must focus on that, because the physics medical link is appeared here. Coefficient of thermal expansion of the restorative material alpha should be similar. Here it's important. Or if you do something less or more, something different from this statement, you will face a problem with your patient. By that, should be alpha, should be all the material should be similar to that of the tooth thermal expansion or contraction. Your filling, the most important condition to your filling to can has opportunity to success, must has the same opportunity, the same, sensitivity, temperature to your teeth, to any human teeth. Let me be more specific. But why? Why? Due to hot and cold foods should not cause separation at the tooth filling interface. Large mismatch in expansion coefficients causes fluids leakage between filling and surrounding tooth. By that, your filling will fail. Here, the delta area will be when the temperature increase or decrease, and we will have delta volume. Delta area equal the area multiple to coefficient, temperature coefficient, multiple delta T, and the coefficient of volume expansion equal V between two brackets 3 coefficient temperature multiple delta T. Here at the last slide, the temperature measurement tools. We know it now. We have three important units: Celsius, Fahrenheit. The last one, it was Kelvin. Now let's learn how we can calculate them by using these three different tools: thermometry, thermistor, thermocouple. Thermometry, all of these have different sensitivity to the temperature, have different material depending. Let's take a close look to them. The first one, thermometry, this one, or which one you will use to determine your patient temperature. It's focused on the molecular mercury, or alcohol. Here, mercury or alcohol. No one another these two liquids. It's perfect to measure the patient and room temperature. It has a good sensitivity with small range of temperature change. In a fever thermometry, a temperature increase case, the alcohol or mercury to expand more than the glass. That's mean mercury or alcohol has sensitivity more to temperature more than the glass, the cover of this thermometry. By that, the glass will not change, will not have delta L in the glass of this thermometry, but we will note some change in L, in delta L, to this liquid, alcohol or mercury. We will use it to determine the patient temperature or to determine the room temperature. Here, thermometer has more sensitivity. We can calculate, we can measure a very small amount of temperature change. It's a special resistor dependent on resistance of this tool, not like the first one. It was dependent on alcohol or mercury. Resistors that change its resistance rapidly with temperature. Initially, temperature change cases the thermometer resistance to change. Like I said before, this tool dependent on its resistance and how it's change, how its sensitivity with the small amount of temperature change. Thermometers are used quite often in medicine because of their sensitivity. Like I said before, it can calculate very small amount of temperature change, approximately you can say 0.01 Celsius. Here, this picture illustrates to us the out service to this thermometer, to this tool. The last one is thermocouple. Thermocouple is dependent on its two junction, and it has a different potential. It has the last advantage to it, in my opinion. It has widely, it can determine a wide range of temperature changing, reach can start from minus 190 to 300 Celsius. It's a huge amount of temperature change. Thermocouple consists of two junctions, like I said before, of two different metals. Here we have two different metals. All of the junction, each junction acts a different metal from the other. If the two junctions are at different temperature, that means the thermocouple will start to determine the temperature, which one we need. A voltage is produced that depends on the temperature difference. Usually one of the junction is kept at a reference temperature. It can be used to measure temperature from minus 190 Celsius to 300 Celsius. Like I said before, that's it. It is like a homework, important. It just contains from 2 points. Let me show to you the solution of it. D density PPT, which one? 4.2, like I remember. Huh. The solution is here. We have just 2 points. Let me close the video. See you at the next lectures. Thank you about your watching, your listening. Have a good day. Bismillah.